Hi, Mrs. Bone here. Today we're going to look at metallic bonding, and we're going to use aluminum to do it. So here we have an aluminum atom, and notice that aluminum has three energy levels, and there are three electrons in its outermost shell. So aluminum has three valence electrons, and if it formed a cation, it would form a positive 3 charge. During metallic bonding, the valence electrons become delocalized, and you can see them. They're no longer in that third energy level. They're free to move around. That's what delocalized means. They're not attached to the aluminum atom any longer. They're not bound to it. So when we're dealing with metallic bonding, we have something called the sea of electron model. And metallic bonding is going to be the result of delocalized valence electrons and the electrostatic force. And we'll see what that means in the next slide. But the idea is that aluminum or any metal is going to form a cation by losing all of its valence shell electrons. They're going to be free to roam around and in between other atoms. So this is a general picture of our sea of electron model. And what you see here is you see aluminum cations with a +3 charge. And each one of these atoms basically donated 3 valence electrons to the sea, or the cloud of electrons that are surrounding it. And what you get here is you get a bunch of positive cations surrounded by a negative sea of electrons. And there we have a very strong electrostatic force holding metals together. You get all that positive charge from the cations. That entire cloud of free moving electrons create a very negative, positive opposition there. So this metal is going to be held together. It's going to be very tightly held together. And these electrons are going to be free to roam anywhere they want. They can move around in between the aluminum atoms. They're free to zoom. They don't generally have a specific direction they move in. They're just free to roam randomly. And we're going to use this sea of electron model to explain the properties of metals. And what we see is we have tightly bound cations. They're surrounded by a sea of negative delocalized electrons and very strong electrostatic force holding everything in place. So that's the general gist of the sea of electron model. And what are the properties of metals that we can use this model to explain? Well, we all know that metals are good conductors of heat and electricity. We use metals to cook, to transfer our heat from our stoves to our food. Metals can be heated up to high temperatures, turned into shapes, gold chains, properties, jewelries, many different things. You generally know metals conduct electricity. You don't want to be outside in a storm with a giant steel rod. We put lightning poles on top of buildings to attract the lightning. So we generally know a lot of the properties of metals. There's a few new ones: malleability, ductility, melting points, and so we'll talk about them one at a time. In the sea of electron model, we first say that metals are good conductors of heat and electricity. So let's start with heat. If you had a hot plate and you left something on it, like a piece of metal, like a knife, and you came back 5 minutes later and touched the end of the knife, it would burn you because metals transfer heat. They conduct heat extremely well. And why do they do that? Well, if we think about what temperature is, what heat is, it's the energy of the molecules. And these electrons in metals are already delocalized. They're free to move already. So they're not being held into place by any bonds or anything else. They're already freely moving. So when you apply some kinetic energy to a metal, they can just move. They can transfer that energy very easily. They can move faster. They can move around. They can bounce off. So, and also we would say that metal atoms are going to be closely packed together, those cations, and they vibrate very well, and they can transfer that vibrational energy sort of like a wave. So the entire structure of a metallic bond is very conducive to transmitting heat and even electricity. And of course, if we wanted to do an awesome science experiment, we could all go into my lab room and we could jam metal things into the outlets. That would generally probably not be a good time. Probably get fired. I don't know what's more disturbing, this image or that I drew this in MS Paint, but never mind that. Electricity is simply the flow of electrons. So electrons can flow very well in a metal based upon the sea of electron model. The electrons are delocalized. They're not committed or bound to any specific atom, the valence electrons, that is. And they're already freely moving. They're capable of conducting that electricity. They're capable of flowing very well. And as I mentioned earlier, electrons usually move randomly. But when connected to a battery, electrons in a metal are going to stream towards the positive end. And what we have here is these electrons would generally be doing their own thing. They're going to be randomly moving. They're going to be going wherever they want. But if I were to hook a battery up to this, these electrons are now going to all start streaming in this direction. They're going to be conducting electric current. So we say that metals are extremely good conductors of both heat and electricity. Metals are malleable. And what does that mean? Well, malleable just simply means being capable of pounded into thin sheets. Think aluminum foil. Aluminum foil. We can pound metals into thin sheets. You think about an ionic crystal. You couldn't pound an ionic crystal into thin sheets. It would fracture or break or cleave. And just a little FYI, press here to lock lid. A lot of people don't know this, but on the sides of aluminum foil, you have these little puncture tabs. And if you push both of them in, when you take the aluminum foil out, you don't pull the whole roll with you. So just a little FYI. A lot of people don't know that, oddly enough. And right here we have the difference between, well, let's see, this is what happens if we apply a force to a metal. If you push down on a metal, these atoms can kind of slide down one another. They can slide past one another. They can smush. And the electron cloud, they can like smear. They can keep them in the shape. So you can pound this metal. You can hit it. You can bang it. And the atoms can move past one another because there's this giant cloud holding them all in. And that doesn't happen in an ionic compound because when you're hitting a metal and this whole area, or when you're hitting an ionic crystal or a compound, this is going to slide down. And if you ever have any point where these two negative charges are going to be next to it, there's going to be strong repulsions. And an ionic compound is going to shatter. It's going to break. But a metal is going to be able to be pounded into small sheets. It's going to be able to thin out. It's like hitting Play-Doh versus hitting glass, if you think about it like that. Except for in this case, the Play-Doh is extremely hard because it's a metal. So we also say that metals have something called ductility, or they are ductile. And that means they're capable of being stretched into thin wire. So if you had a very hard die right here, and you took metal that was, say, softer than your die, and you were to push a big metal rod through this die, the metal would come out in terms of thin wire. It would compress itself. It would stretch into thin wire. So metals are both malleable and ductile. And we kind of know that copper wires, speaker wires, they're all made of metal into these thin little wires. That's how we transmit our electricity, by turning metal into thin little wires. And this is the process by which we do it. These atoms are free to move and slide past one another within that strong electrostatic cloud. And metals have high melting points. We generally know that. Metals are solid at room temperature. If you look at the nonmetals like nitrogen, oxygen, and those other gases, they're all gases. They've melted, evaporated, vaporized. So they're not ever really going to be solid under normal conditions. Metals are all generally solid and pretty hard. And they have very high melting points. And that's because thermal energy is transferred very, very well by these electrostatic forces. And you have a brief assignment based on metallic bonding. Explain to me what an alloy is. Why are alloys useful? And list 3 examples of alloys and their application. What metal is a liquid at room temperature and why? The why part of this could get pretty interesting. So hopefully you enjoy looking at that. And explain the disappearing spoon trick in chemistry briefly. Just tell me what it is, what happens. And hopefully you have a better understanding of metallic bonding. Delocalized valence electrons freely moving. You have positive cations in the center and a sea of electrons surrounding it all electrostatically, holding it all together. Very strong bondings. This is Mr. Sapone. I'm out.